Hello, this is AMET 104, lecture recording week 6.2. So today we're going to do the exam review. This is for the exam 1. So far we have done entire chapter 9 and the entire chapter 10, and we went over so many different formulas and different examples. Initially, I thought it may be beneficial to go over different examples, but so far we've actually done so many examples, and within this short period of time, I don't think it'll be as beneficial to go over, because if I do, I will probably only be able to cover maybe 5 problems tops. Instead of that, I thought it may be more beneficial for you if I go over a concise review on different formulas used in chapter 9 and chapter 10, and briefly talk about where and how it is used. So without further ado, let's start that. So first, chapter 9.1 was sequence and population sequences. So sequence is by definition the infinite list of numbers. And in chapter 1, we have, chapter 9.1, sorry, we went over just different notations, where a generic notation will be a sub 1, a sub 2, a sub 3, and so on, all the way up to a sub n. Where here, a sub 1 is the first term, second term, third term, all the way up to nth term. And it will continue on like that. Population sequence is the same thing, but it simply describes a population of some sort. In this case, population sequence is notated as P0 as initial population, and P1 as population after 1 generation, P2 as population after 2 generations, and so on and so forth, and Pn will be population after n generations, and it continues on. And that was actually the end of chapter 9.1. So in this chapter, all we had to do was to simply be able to understand the definition, and given a formula or some type of sequence that you are given, you just have to understand what type of sequence it is and how to express it in explicit formula or recursive formula. I'm not going to go over the the definition of explicit formula and recursive formula, because it will be self-explanatory in chapter 9.2 and 9.3. So chapter 9.2, it was the linear growth model. So in the linear growth model was when simply the population sequence or population growth model is simply linear. In other words, it increases by the constant number. So normally you would see something like p sub 0 plus d, p sub 0 plus 2d, and so on and so forth. So the explicit formula is actually given as p sub 0. Let me actually say p sub n. So this is the nth population is defined as the p sub 0 plus nd. And recursive formula is given as p sub n equals to p sub n minus 1 plus d. So as you can see, the explicit formula is defined by the explicit generation n, whereas the recursive formula is defined by the previous term. So when it comes to explicit formula, you can simply plug in the number n into the formula to find the nth generation. So if you want to find the fifth generation, the population after fifth generation, you would plug in 5 in there. So here, the notations would be p sub 0 is initial population, and here n is the generation, and d here is called the common difference. So in the exam, as we have already experienced in quizzes and homework, if the problem wants you to use the linear growth model formula, they will tell you what type of growth model it is. So they will explicitly mention that it grows linearly or grows according to linear growth model. So make sure you read the problem several times just to understand that it's if it's asking for linear growth or some other type of growth models. So one other thing that we did in chapter 9.2 was arithmetic sum formula. And that is given as the sum, which is simply P0, P1, P2, all the way up to Pn minus 1. And as you can see, this is n terms. It is n terms because if you count from 0 to n minus 1, there are n terms here. It is defined as the initial population and the last term in the sequence, and you simply multiply that by the number of terms and you divide by 2. The notable example with this one was making tractors. We were making tractors and we were to find out the cost of storage. And we also did an example where making street lights and the cost of operation for the next 2 years. And those are the type of examples that you may encounter. So that was the end of chapter 9.2. Let's now go over chapter 9.3. And this is the last chapter of chapter 9, or last section of chapter 9. And section 9.3 was the exponential growth model. So the first thing that we talked about here was the growth rate. So the growth rate. Exponential growth is different from linear growth. And as you can see, this, according to it just grows by the exponential, with exponential behavior. And hopefully this will make more sense after I go over some formulas. So the growth rate R is given as y minus x divided by x here. And here, y is the end value. And here x is the baseline. So this is simply defined the growth rate if you went from x to y. That's all there is to it. The exponential growth grows as such. So P0, the initial population, and P1 is R multiplied by P0, and P2 is defined as R to the power of 2 multiplied by P0 plus P3, it's not the plus, equals to P3 equals to, and P3 equals to R to the cubed multiplied by P0, and so on and so forth. So this would imply the initial population after 1 generation, 2 generations, 3 generations, and so on and so forth. The explicit formula is defined as P sub n equals to R to the power of n multiplied by P0. So here, simply to find the population after n generation, all you're doing is taking this and plugging in the number of n into this formula. That's all we're doing. The next thing we did was the recursive formula. And the recursive formula is given as R multiplied by P and minus 1. So simply, you're taking the previous term and just multiplying the R. So what does each term represent? So here P0 is initial population. And we know that n is the generation. And lastly, R here is the common ratio. And also R is defined as 1 plus the growth rate. One thing to note here is that if R is greater than 1, then it is increasing. If R is between 1 and 0, it is decreasing. And if R is 1, it is constant. And lastly, if R is 0, it's a 0, or I use the word total collapse of population. And similarly up here, apologize for going back up to the previous chapter. Here, when you're looking at the common difference, if the D is greater than 0, then it is increasing. If D is less than 0, then it is decreasing. And if D is 0, means it's a constant. One last thing that we looked at here is the geometric sum formula. So geometric sum formula is the sum equals to P0 R P0 R squared P0 dot 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 plus R and minus 1 P0, which in other words is the same as saying that P1, P2, all the way up to P and minus 1. It's the same thing. And that is defined as the common ratio to the power of n minus 1. You multiply that by the initial population, and you divide it by the common ratio minus 1. And you should also know that here there are n terms. So there are a notable example that we did here was if you get a penny today, if you get 2 pennies tomorrow for the next day, and so on and so forth, after 31 days, how much would you have? And that was a notable example. So that was the end of chapter 9. That's all we really did. Excuse me. As I mentioned before in 9.2, it's the same in 9.3. If the problem wants you to use the exponential growth model, it will certainly tell you that in the problem itself, it will have a language saying that the population grows or decays according to the exponential growth model or linear growth model. And just by simply being able to read that language, you should automatically know, and it'll help you to understand which formula is more appropriate to use for that specific problem. So let's now go over chapter 10. So chapter 10 was the financial mathematics. And here we actually used a lot of the techniques that we learned in chapter 9 as well. So 10.1 was percentages. So when it comes to percentages, there's really not much to talk about because I'm sure everybody understands how to convert to percentage, to decimal, and to fraction, and so on and so forth. It's a really critical and useful technique, but I'm sure all of you know. So just to write something down, if it says X percentage, it is simply X over 100. And that's really it. That's really all there is to it. So let's say, actually, let's just say P. If it's P percentage, it's simply expressed as P over 100. And to express the, this is to express the percentage to decimal. And if you simply put this into calculator, is it to fractions, sorry. If you simply plug this into calculator, you should be able to get a decimal as well. So simply by dividing P by 100, so divide P by 100 to get decimal form of P. What else did we do here? So we also did okay, so I think we also did the final value. So same as here, the percentage increase. So increase or decrease is given as P, and this is the lowercase p, and decimal was given as F minus B divided by B. And that was exactly the same as saying F over B minus 1. And that also tells you that knowing to find the baseline, you can simply get to the F over 1 plus P. And that's all the same formula. And this is actually derived straight from this growth rate. That's what it is. I'm just using a different notation just to have you understand the F here is the final value, and B is the baseline, and P is the percent in decimal. But yeah, that's it. Chapter 10.1, we really only did different definitions and nothing new was really learned there. So chapter 10.2 is when we actually start doing some mathematical finance here. And this is the simple interest. So simple interest is when the interest rate is applied only to the principal. And the interest paid on the loan per unit of time is constant. So the formula goes as such. So the simple interest formula. Is given as I equals to PRT, where here the P represents the principal, and the principal here is the total sum of money that you owe. R is the APR in decimal. And lastly, T is the number of years. And the future payoff in other words, the total amount that you owe is given as F equals to P plus I, which makes sense because the future payoff would be the principal, the money that you borrowed, and the interest on top of it. And you can simply express this as P plus P RT, or simply P multiplied by 1 plus RT. They're all the same formula. Simple interest is a very good way to start thinking about how the interest works. It's a very simple example, and it's a good examples to really get your feet wet. However, in real life, simple interest is really not very applicable because not many places really offer simple interest. So we're gonna talk about the compound interest now. So 10.3 is the compound interest. So here with the compound interest, not only does the principal generate interest, so does the previously accumulated interest. So the notable example that we did here was the trust fund account. So when your parents deposited X amount of money into your account when you're born, let's say when you're 18 years old, how much has that generated? Or when you're 60 years old, how much is it? the annual compounding formula goes as like this. So annual compounding formula is given as f equals to p multiplied by 1 plus r to the power of t. Here, f is the future value. And p is principal. R is the APR in decimal. And T is years, number of years. So you use the annual compounding formula when the interest is generated once a year, or the interest is compounded once a year. And you'll see in the examples, you'll see in the problems that it'll say that it is compounded annually. If you see the language annually, this is the one that you need to use. It'll actually directly tell you what kind of compounding it is. And they will also say that most of the time it'll state that the interest is compounded at the end of each year. That is to avoid any confusion on problems where if it's compounded for 5.5 years, because it's not reached the full 6-year mark, it only has accumulated 5 times instead of 5.5 or 6. So now let's look at the general compounding formula. General compounding formula. General compounding formula is simply used on most compounding situations. And it is actually really similar to the annual compounding formula. You simply write p multiplied with 1 plus the lowercase p to the power of t here. And here, f and p is the same, so f is the future value. And p is the principal. And lowercase p is the periodic interest. And t is the total number of compounding. Total number that it's compounded. So a couple of things to note here. The periodic interest is actually defined as the R divided by the number of times it's compounded in a year. Compounded per year. So here, obviously, R is the APR in decimal. And simply, so if it's semi-annually, you would divide by 2. If it's quarterly, you'll divide by 4. If it's monthly, you divide by 12. If it's daily, 365, and so on and so forth. And make sure that R is in decimal. And T is simply the number of years, and you multiply by number of compounded per year. So for example, if it's been compounded for 2 years monthly, you would multiply 2 by 12 and the t will be 24. And in the problem, as I stated before with the annual compounding, it will have a language. It will tell you what type of compounding it is. It'll tell you if it's compounded monthly, daily, weekly, bi-weekly. It'll tell you everything. So make sure you read the problem multiple times just so you understand the formula that you need to use. There is one more type of compounding that's a continuous compounding. Continuous compounding. So the formula is as such. So continuous compounding is simply saying that it is compounded infinitely often over infinitely small compounding periods. So it's being compounded more frequently than once a minute, once a second. It's actually being compounded every period of time. I don't know how to put it nicely, but simply it's the type of compounding that generates the most interest. So given this formula, we know that already that f here is the future value. P is the principal. R is the APR in decimal. And lastly, T is the number of years. I don't think there's anything else that we need to go over about the continuous compounding. It was pretty self-explanatory. And here E is the constant. It's Euler constant. And found in your calculator. One last thing we did in this chapter was the annual percentage yield. Annual percentage yield. And often it is abbreviated to APY. Simply saying that this basically tells you is the annual percentage increase on the value of an investment and that's all there is to it. And APY actually has two different formulas. So the APY For general compounding, or annual, so in other words, when the compounding happens finite amount of time in a year, APY is given as 1 minus R divided by T to the power of T minus 1. And when it's continuously compounded, sorry, this pen is a little finicky lately. Continuously compounding. You would be given APY as simply e to the power of r minus 1. And here we know that r is the APR in decimal, and t here is the number of times compounded per year. One thing to note is that I'm sure all of you remembers this, that more frequent compounding yields more interest. So monthly compounding would yield more interest compared to the annual compounding. And continuously compounding will yield interest the most. So in chapter 10.4, we did the retirement savings. So we use the language retirement savings. However, it is simply saying that it's a recurring investments. Let me actually put that here. It doesn't really have to be under the retirement savings context. Anything that you invest as a recurring investment or contribution, that can be used the same. You can actually use the same formula to find that. So recurring investment contribution. So we went over a couple of different formulas. So the retirement savings formula had two different formulas, I think, yeah. So the first one that we did was the yearly one. Savings formula. And this is the annual version. And that is given as V equals to P, and you multiply by 1 plus R to the power of Y. And you take away 1 and divide everything by the R. Here, V is the total value of the account. And P here is the annual contribution. And if you have R, that is the APR in decimal. And lastly, Y is the number of years contributed. So here, you can actually be asked two different types of problems. You can either be given the annual contribution amount and you're asked to find the total value of the account after Y years. Or they can also ask you under the given terms, if your total value of the account is V amount, how much do you have to, or how much have you contributed each year? And those are the two types of problems. And I actually went over multiple times in the previous videos, and I think it'll be beneficial for you to go over that again if you can. And basically the same formula, but there's a monthly version. And that is V equals to M multiplied by 1 plus R divided by 12 to the power of T minus 1, and divide everything by R12. So here you can simply just write R divided by 12 as just the lowercase p as periodic interest. I just wrote that because it's a monthly version. We're not going to talk about daily version or weekly versions or anything like that. But this is the type that we use when you're doing monthly investment as opposed to yearly investment. In real life scenarios, this is more likely because most people just use 401k or just save a little bit from each of their paycheck that they have. So here, simply V is the total number of payments, total value of the account. And obviously the P is the principal, M is the monthly contribution. And you have R as APR in decimal. And T is the total number of contribution. And similarly here, we can be asked this, two different type of problems. You're either given the monthly contribution amount and the terms, and you have to find the future value or the total value of the account, or you're either given you're given the total value of the account first, and you have to find the monthly contribution. And all you have to do is just manipulate the formula and use some simple arithmetic and use your calculator to find the correct answer. So we're almost done. We only have one more chapter to go over. So that's chapter 10.5, and that was consumer debt. We only talked about the installment loan here, and that's all we're going to talk about. Here we only did one formula, and that is the amortization formula. And amortization formula is, sorry, yes, that's right. Yeah, amortization is simply when you're financing. We often say we finance a car, or we finance a house with a mortgage loan, and those things are called amortization. It's an installment loan, and it's a form of a loan where you purposefully borrow money and repay periodically. So here is the formula. M equals to P, and you multiply by the lowercase p, 1 plus the lowercase p, to the power of t, and you divide it by 1 plus lowercase p to the power of t minus 1. I think this is the most complicated formula that we've done, but at the same time, we've recently done this, so I hope your memory is very fresh. And here, M is the monthly payment. And P is the principal, or in other words, the total amount of loan that you're taking out. And the lowercase p is the monthly interest. Or in other words, this is the same as R divided by 12, where R is APR in decimal. And P and T is the total number of payments. And similarly here, we can be asked a couple different type of problems. We can either be asked if the total amount of the loan is P, under these terms, how much is your monthly payment? Or you could also be asked if your monthly payment, if you want your monthly payment to be this much, how much do you have to take out? Those are the two different type of problems. One tricky example that I did with the consumer debt was the refinancing of the house. And so I actually went over the example, and that exact example, but you should be able to find the example in the textbook. If you go on your Pearson, there's an e-textbook. I'm sure most of you have used it already. And there is one example with all the answers in there that they go over how the refinancing works. Please go over that. That may be beneficial for the exam. It's the most tricky type of problem that you could encounter in this chapter. Okay, so I think that's it. I think that's all the formulas that we have gone over so far, and I guess that's it. Well, good luck, and thank you for joining the class. Have a great rest of the day.